Welcome back to Multigrid Methods. Today we're talking about the convergence of the General Symmetric V-Cycle. So in this result, we want to show that if we do more smoothing iterations, then our convergence rate improves. So that's the idea. We needed a technical lemma for this result, which we proved last time. We stated and proved this last time. I'll review what it says here. We won't go through the proof. But we need this technical lemma in order to show the convergence for this symmetric general V-cycle where we're having a number of smoothing operations or iterations which is exceeding greater than or equal to 1. And we're going to show that if we have more smoothing operations, then we're going to get a faster convergence. M is usually the parameter that we use to denote the number of smoothing iterations that we're doing. And so it shows up in, for example, places like that. This is the technical lemma that we stated and proved last time. If smoothing is done with Richardson smoother, remember Richardson smoother uses a constant iterator or a matrix, which is basically diagonal with some, I guess all iterators are constant, but what I mean is that it's just some number times the identity. So it's just some diagonal matrix with uniform diagonal entry. So it's kind of the simplest of all possible smoothers that you could use. This capital lambda L is a number which is greater than the spectral radius of the stiffness matrix, but less than or equal to a constant times the spectral radius. And this CR number is just some number which is greater than or equal to 1. The ideal case is that it's equal to 1 or just a small number close to 1. Oops, I'm sorry about that. Okay. And in that case, then we can show this estimate that if we see an object like this matrix appearing on the left-hand side in the AL inner product against a common vector, then we can approximate the size of this by 1 over 2m. Remember, KL is our error transfer matrix for smoothing, and it's always I minus S L times AL. That's our error transfer matrix for smoothing. That's what appears in these locations. And of course, I minus that is of course just equal to SL. In any case, if I see this matrix, then I can replace it by effectively a 1 over 2m times this matrix. Okay, and everything else stays the same. It's the same inner product and the same vectors appearing on both sides. So we showed last time that this was due to some sort of telescoping property. It was a combination of a stability property plus some sort of telescoping property where we took copies of things like this and we used a stability estimate that we derived here. And we take each one individually and replace it by a slightly different stability estimate. So for this stability estimate, we're using KL to the 0 power, KL to the first power, up to KL to the 2m minus 1 power, so that there are 2m estimates that we're using in a row. And then we showed some sort of telescoping property in order to get the estimate that we want. Okay, and then to finally, I guess we're almost at the estimate we want. All we have to do is divide both sides by 2m and we've got it. All right, so here's the general convergence result that we want to prove. It's a result due to Braess and Hackbusch, and therefore it carries their name. Suppose that assumptions G1 and A1 hold. So G1 is the weak Galerkin approximation, and A1 is the weak approximation property. So it turns out we don't need the strong approximation, we don't need the strong Galerkin, but if you want to replace this with strong Galerkin, so in other words, the wrap condition, and if you want to replace this by just the A0, the strong approximation property, then since those results are stronger than either of these two, the same result's going to still hold. V-cycle, of course, means that P is equal to 1, and we're going to symmetrize smoothing so that we do the same number of pre-smoothing steps as we do post-smoothing steps. Now, the last result, we set M equal to 1, and we proved that we get convergence, which is kind of a remarkable thing. Here we're going to try to show that we get an improved convergence if M is greater than or equal to 1. Or specifically, if M is strictly greater than 1, we get an improved convergence. So the convergence rate we want to establish is this one, capital M over capital M plus little m. M is the number of smoothing iterations. Capital M is a constant, so it's CA1 squared times CR squared over 2. So it's a little bit smaller than the constant that we proved in the previous results. So this is an improved result for sure. And we see that M now is not equal to 1, so we can improve the convergence rate. This whole number, you will observe, is a number which is less than 1 strictly, and it gets smaller as M gets larger. And in fact, we can make it as small as we please because we can make M as large as we want. Now, of course, there's a point of diminishing returns, as we've talked about previously, because if I take more and more smoothing iterations, there's a cost to that. And it turns out it's a little bit something like this. We can map the cost or the floating point, total number of floating point operations that we would need to do to get the convergence result we want. And we can plot M on this axis, and there's going to be some sort of trade-off curve like this, so that there's going to be some minimum where we max out. And this might be something like M equals, I'm just going to guess here, M equals 4, something like that, M equals 5. But if we do more iterations than that, it's going to be more expensive than it would have been actually to do less, because we're going to get we're going to converge with a fewer number of floating point operations. In any case, we just have to keep that in mind as a practical method. Otherwise, as a theoretical device, this says that we can make the contraction factor as small as we want. So the proof is similar to what we did in the last theorem. Remember, we broke the error into 2 terms, and we estimated one according to some idea, and then the second one according to a slightly different idea. Effectively, it's like splitting the error into something which looks like an error for just a 2-grid method, and then the error associated to multigrid. So this is kind of 2-grid error, and then this is the perturbation to that, because we're not actually doing the 2-grid method, we're doing multigrid. So that gives an extra little error, but that extra error is confined to this term T2. So let's see how this goes. So we're going to begin with an expression for the error propagation matrix. So we showed way back in the beginning of chapter 5 what this guy looks like in terms of symbols. So EL is, we've got a part here which looks like the error related to or associated to the 2-grid method, plus the error related to everything else. And I think I may have a typo here. So it looks like I'm missing the factor of an M here. So is that a typo? I think it is. I think there should be an M on that guy. And we see that the error associated to multigrid at lower levels is given by this term here. Now, previously, we had a P on this term. And you might say that there's an error because the P is missing. Well, remember, for V-cycle, P is exactly equal to 1. So we can just assume that the P is taken care of. So this is the expression for our error. And it differs from the one that we looked at previously only in the inclusion of this M here and here. And I believe I'm missing one there and there. Okay, and so this is the error at the lower level. KL, of course, is the error transfer for smoothing. And because my iterator matrix is symmetric, this is equal to its own adjoint with respect to the AL inner product. Remember, star means adjoint with respect to AL inner product.
Dr.
And
Wise,
yeah,
is it is there an extra PL minus one in the second term?
this one here. Let's see. I think I might have an error, a typo on that one as well. I think it's either an extra one or I'm missing a transpose on that guy. So I think, should it be transpose?
I'm thinking that it's the second one is extra,
Okay.
but I could be wrong.
Oh, no, 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 no. Okay, so this one is correct. And you're saying this one might be incorrect.
I think it's extra. Yeah.
Okay, let's go back and look at the one for the simple symmetric V-cycle. And if we can't resolve it there, then we can go even further back. So yeah, it looks like an error. It shouldn't be there, right? So this one is, yeah, this one, I was thinking R, but okay, so this guy is correct, and that guy shouldn't be there. Is that what you're saying? I think that's right.
Yes. Yeah.
All right. So let's see. Now here, oh, let's see. Okay. Let me go back. I need to go back one more time. Bear with me, but I want to make sure this is correct. So EL minus 1 pi L minus 1. Okay, let's check what I had previously. Yeah, okay. I was wondering if I got that one right, but yeah, that makes sense. So one thing to do is just to do a sanity check and make sure that everything is compatible for matrix multiplication. So this one is L minus 1 by L. So it can multiply that on the right. Yeah, that's clearly wrong. And this is L minus 1 by L minus 1 square matrix. This is L by L minus 1. Okay, so now at least it makes sense with respect to matrix multiplication. Okay, thank you for that. Great, good eye. Okay, so where was I? Talking about the error transfer matrix for smoothing. That's this K matrix, where it doesn't really matter too much. I'm just reminding you here that this lambda L is of course satisfying these this inequality, this double inequality. And this is only needed because of the telescoping estimate that we just showed. Okay. Well, it's needed for let's see, am I assuming any smoothing property? Not any separate smoothing property. We're assuming Richardson smoother is being used. So that means that we're going to be able to use this telescoping estimate here. But it also means that either of the properties that we had before apply. So either this first smoothing principle or the second smoothing principle. Okay, because Richardson's smoother satisfies them both as long as I make that choice. As before, we're going to set up two terms, T1 equal to IL minus pi L tilde, WL. And that's just associated to this term once we compute this guy and use the fact that we can, that this guy is is self-adjoint. Okay, it's self-adjoint. So we can move it to the other side. And so we'll quickly get this definition associated to that term, where WL is equal to KLMUL. All right. The other term, T2, is all of this, except that we need to make a correction, right? Actually, this one is kind of, let's see, what In what sense is it weird here? So it's EL. So this should just be pi L. Pi L minus 1, right? And let's, if we go back and check the simple symmetric V-cycle case, so the TL would be, or the T2 should be the same there, except for the number of smoothing iterations. Yeah. So PE and then pi L minus 1. Okay, so pi L minus 1 should be there. The WLs are KL raised to the n power times UL. And in that case, now we're finally correct that this this thing that we want to bound is equal to T1 times T2. Now, I should add this guy is because EL is self-adjoint positive semi-definite in this inner product, then this whole term has to be positive, well, non-negative. So just if I can show that this is small, that doesn't necessarily mean anything unless this thing is already a positive number or a non-negative number. It's getting squeezed between this number, which is getting small, and 0. Okay, so that's our basic construction with these corrections. So let's attack T1 first, and this is fairly similar to what we had last time. Okay, so owing to the weak approximation property, so that's the A1 property, we get this line here. Okay, so that's, if you look at what weak approximation property says, it's exactly saying that this object is less than that. That's property A1. That's our approximation property. And we keep in mind that multigrid, for the proof of it, always requires 3 pieces. It always requires an approximation property, some sort of Galerkin condition, and some sort of smoothing assumption. Here we're assuming that we are using Richardson smoother, so we get a lot of, we get either the first smoothing principle or the second one. It doesn't matter which one we want to use. Whichever one's going to be more useful to us is the one we can use. All right, so now let's unpack this. So we've got a string of equalities here. So this is just a bunch of unpacking that we need to do. So I'm not going to bother with the constants. The constants all stay the same until this point where we replace KL with the definition of KL, assuming that we're using the Richardson smoother. All right, so what are we doing in this first line? The first line, we're just replacing WL with its definition. It's KLMUL. We're also, let's see, so this estimate, notice that we start by using the AL inner product, but we end up using the L norm. Okay, the L norm. So we replace this with this definition. We use the definition of the L norm squared. Okay, and so that's just an inner product involving the same vectors. Now, what we can do is some manipulation involving this A matrix. We can throw this guy over on the other side. And remember, it's symmetric, so we get AL squared, not AL times AL transpose, but AL squared. All right, what's next? So now we can take, and I'm not sure why I didn't do this, didn't do it differently. I could have just pulled this guy down. In fact, I think I will probably correct the notes to simplify that. We could have just taken this guy and pulled it down immediately. I didn't realize I did something a bit more strange. So I first moved it over here and then I pulled it down. That's not necessary. So I can just eliminate that extra line there. I can pull either one of these guys down, you see. I'm going to pull this one down. So that line doesn't need to be there. Okay, so that's what I did there. And now I'm going to use the property that says that AL, well, let's see. So we have KL, that's equal to I minus pi L inverse times AL. So now if we do I minus KL, that's just equal to pi L inverse times AL. So if I multiply and divide A by pi L inverse, then what I can do is replace an AL with I minus KL times pi L. Okay, so it's pretty easy to see that I can take this AL and replace it by IL minus KL divided by lambda L. Okay, so now I can move this guy back over to here. It's going to move over with an adjoint because I'm using the AL inner product. But I keep in mind that this guy is self-adjoint and it is, remember, well, I don't know if it's a remember or if it's just observed that this KL matrix, once I move it back over, is associative or commutative with this, it commutes with this matrix, so I can just move it past that matrix into here. So the KLM that was here first moves over here, and then it moves over here because of the commutative property. Okay, it's commutative with this matrix. It's very easy to see that, and because that thing is only what? That thing is only something like the A matrix anyway. Okay, so if you buy that, then the next thing we want to do is use the estimate that we just invented, our little technical lemma that we described as our telescoping technical lemma, and that allowed us to take the 2m that was here, move it down here, and change this product to that. Okay, so that's that estimate 16. I could click back to it, but we were just there, and I think you probably remember what it was. Okay, so what estimates have I used so far? Just two. Uh, we've used our approximation property. Weak approximation property is all that we needed, and we used our telescoping estimate involving the Richardson smoother. That allowed us to bring this 2m down. The next step we want to do is, if we observe what this guy is here, we're going to apply one of our smoothing estimates involving the Richardson smoother. Okay, so I forget, and I should have written which one this was. So let me put a question mark there. I would like to put that reference on there. But one of the smoothing principles that involve the Richardson smoother is going to give us this estimate here. Okay, so let's apply that now. And then we're going to set gamma equal to m over m plus little m. So notice that this is precisely the parameter here is the parameter m, okay, capital M. And this term here can be rewritten as just a very simple exercise because we can use the linearity of this first component. We can write this as UL, and AL inner product. And then what's left is just going to be KL times UL to KL to some power, and that's just going to be WL. Okay, so this is a simple identity. Okay, so now exactly as in the proof of the last theorem, an induction argument is going to be what we're going to kick in next. And the details are very, very similar, so we don't have to go through them. It's really more or less exactly the same. I probably should have included a nice little problem exercise to show this, but I'll simply say it now. You don't have to do this as homework, even if I squeeze it in later, maybe a homework exercise. To show that exactly the same steps that we employed in the proof of the symmetric V-cycle convergence, the simple version, can be used in the general version. To show that T2 is less than gamma times this quantity, which is the quantity that involves the smoothing matrix, the error transfer matrix for smoothing, minus gamma times T1. And if that's true, then you can put these two facts together pretty easily. Okay, so if that's true, then what we do is we know that that's just T1 plus T2. We're going to split T1 into 1 minus gamma T1 and gamma T1 plus T2. We're going to use our 19, which is this guy, to replace T2 by that object there. And then we're going to use 18 to finish up and approximate T1. And this guy is the only thing that sort of lags behind. That guy comes out here. If we add up everything that has to do with T1 and then estimate and replace it with all this stuff and a little bit of algebra, we get exactly the result that we want to show. Okay, so this part here is 2 steps. So let's recap. So we did approximation property. We did that new telescoping sum property. We have our smoothing property. And then when we do T2, we use the same induction or induction type argument that we used previously to get this. And then we combine them together to get the result that we want, which is the contraction at the rate gamma, where gamma is this parameter here. Okay, so I won't go through all the gory details because it is fairly similar to what we had before. The big technology that we brought to bear on this is precisely that telescoping estimate. So that thing is the new piece. Otherwise, there's nothing new. Okay, so now, as before, this by itself doesn't represent a convergence estimate. This estimate that we have here doesn't appear to be a convergence estimate. But what we want to show now is that actually that is a perfectly good convergence estimate. And there's nothing to do here really as well either, because the details are fairly similar to what we did in the proof of the simple symmetric V-cycle at the very end. So what do? We used the fact that the error transfer matrix was self-adjoint positive semi-definite, and therefore it has a basis of eigenvectors that form an orthonormal basis with respect to the AL inner product. And we use that fact to show that the error estimate that we just derived, which isn't really an error estimate, can be turned into something which is an actual error estimate. So those details are also exactly like the proof of the last corollary. So somewhere back in here. So I won't go through those details either. So I just want to emphasize, I will just have to check a couple of things. Let's see. A1. So I believe this is still correct because right now over here we're using the parameter CR, and here we're using CS2 squared. But I think, and I'm going to have to go back and check this, that CS2 squared is equal to CR. I need to go back and check that. And for consistency, I ought to at least say something about it, but I believe that's true. It's just my memory is failing me at the moment. All right, so that's it. That is, in a nutshell, the multigrid process. So here in chapter 5, our methodology was the following. We did all these assumptions and we said there's not necessarily any underlying PDE that we're solving here. There's no finite element method. There's no finite difference. If the system or the method satisfies these various assumptions, then we can put them together in pieces and we can prove the convergence in the following way. The important thing about multigrid type convergences are that this contraction factor here, M, is absolutely independent of L. So this works on any level. So the nice thing is we get a contraction no matter how fine we make our mesh spacing. So that means, in other words, how large this L is. So independent of that, we're always going to get a contraction which is at least as good as the contraction predicted by this rate here. And it can be improved in this case by making the number of smoothing steps larger. So that's the key technology that we've uncovered with this theory, that we can get a contraction rate which is completely independent of the mesh spacing. And that is not true for a general linear iterative scheme that you pull off the shelf like Jacobi or Gauss-Seidel, things like that. We know that as you make the mesh finer and finer, the convergence rate is going to deteriorate. And so that's not good. Here in multigrid methods, we don't get a deterioration of our convergence rate because we can prove these things completely independent of L. All right, so now I want to go back a little ways back into the early parts of chapter 5 because I made a couple of changes that I want to mention and that I think are important. So we introduced previously a strong and a weak approximation property, but for a convergence that we're going to derive for the cell-centered method in a later chapter, it turns out we need another type of weak approximation property that we didn't have previously. So those of you who are interested in cell-centered multigrid should pay particular attention because these changes are associated with that. Okay, so the first two approximation properties are completely the same as before. We had this assumption A0. So remember, this used to be like A3, and this used to be A4. So, but the names were still the same. The strong approximation property and the weak approximation property. So, now why they were called that was because if I assume this and I have the Glerkin condition, then that implies the weak approximation property. Okay, so we understand that. But what about this new property I've just introduced? So this one is brand new, and it's called the alpha-weak approximation property. So the multigrid algorithm satisfies the alpha-weak approximation property, also called assumption A2, if and only if there is a constant alpha, which is between 0 and 1, not including 0, such that for all UL in RNL and every level, I minus pi L tilde, so this is the error in the coarse grid Ritz projection, times UL against UL in the AL inner product is less than all this jazz. Now, what is that stuff? The first part looks a lot like this part here, except with a slight change. Looks like this part, but where I'm using only half of that, or only the fractional power, the square root of it, right? That's all that stuff. Or some power of it, maybe 1 over alpha power. Nope, that's not quite right. That's what I'm doing, taking the alpha power of those, where alpha is some fraction. That's sort of what I mean. So notice that if alpha is equal to 1 here, then I just return to this. Say alpha equals 1, I get all three of those, and this guy disappears. So this is somehow new, and it's different if alpha is different than 1. So alpha equals 1, that's just a weak approximation property. But let's say alpha equals a half. What do we get here? So if alpha equals half, I just get this to the first power. I get a constant to the first power, but it's a constant. It doesn't matter. This guy here matters because this is going to be the square root of the spectral radius. Okay, remember alpha is equal to a half here. And now this thing is new. UL in the AL inner product, or sorry, the AL norm. And if this is a half, then 1 minus alpha is a half times 2 is 1. Okay, so I get this guy is new and it comes at the 1 power. This is at the 1 power and everything else is as I mentioned. So this is kind of different. It's what we call an interpolation. So this is interpolated between this value here and this value here. Okay, UL AL. Okay, and should I say square? Yeah, square. So it's somehow an interpolation between these two things. This turns out to be highly useful to us for proving multigrid convergence, and this will not be so useful. So the question is, if I interpolate between these values, alpha is our interpolation parameter, it's a power, will I get something useful for convergence? Well, it turns out for some of the methods that we exhibit, some of the multigrid methods we exhibit, we can only show an inequality of something like this interpolated inequality, where alpha is some parameter which is between 0 and 1. If we have something like this and we call this an alpha-weak approximation property, and the good news is we can still show convergence even if we have something like this. Okay, so we can still show convergence. So that's a new definition. It wasn't there previously. I updated the notes and the lecture slides so that this is now included. This new assumption A3 or A2. And that's what originally had prompted me to start thinking about changing the assumption numbers, because I thought if I ever want to add another assumption, then I have to change all the numbering. So for example, if I want to add another Galerkin assumption, I have to change all the numbering for all these assumptions and all the smoothing property or smoothing principle assumptions numbers as well. And that would be highly problematical. So I thought I need to make this change now. So I changed the numbering system here, and the whole goal of that was to add this assumption A2, which I've now done. So now you might ask, well, why the heck did you add that? What's the deal? And is this interpolated inequality useful in any way? So let me show you now that it is useful and it does give us a convergence. So now this is chapter 5, slide deck 1. And it's been updated on GitHub and on Canvas, so you can follow along with this updated version. And now I want to show you in chapter 5, slide deck 2, which is what we just came out of, where I'm going to apply this in a couple of instances. The first one is in the true grid convergence result. So let me go back to grid convergence. We proved here under the standard assumptions. That all stays the same. There's no change there at all. So you can go through the proof of this. It's not long. There's only a couple of lines. You remember you use the Galerkin principle, and that gives you something. And then you have to use smoothing, and you have to use the approximation property, which is what we did. So then we had these stability properties. I had to move those because I'm going to use those stability properties in a moment. I actually had to use them earlier. So these stability properties that used to be in the W-cycle convergence section, okay, which is here, I had to move them up a little bit. And that's because that allowed me to prove this result, this alpha-weak convergence of the two-grid method. So this guy is brand new, and I want to go through this. All right, this is in the case, of course, if we had alpha equals to 1, then that's just the weak smoothing or weak approximation property, and everything still works in that case. So the new thing here is that we're going to use alpha weak, and we're not going to necessarily assume that alpha is equal to 1. All right, so suppose that, what do we have? The strong Galerkin condition holding. Alpha weak approximation property, that weird interpolated approximation property. And we're going to suppose that smoothing is performed via the Richardson's method. So here you might say, well, where's the smoothing property that you're assuming? Well, if I assume that I have Richardson's smoothing method, then I can apply either the first smoothing principle, which is all that I have up to this point anyway, or I could use the second smoothing principle and anything else that I derive that is basically associated to using Richardson's method. So Richardson's method buys me a lot. Well, then I can prove that I have convergence of my two-grid method. The only thing is that my convergence is reduced a little bit. So previously, I had this where alpha was equal to 1. If I have alpha weak, I can still prove convergence, but I prove it at some fractional power. So here's the idea. Suppose that I have alpha equals to a half. And let's say I do my computation so that I make this equal to 1/4, 1/4. So my gamma contraction factor inside of here, I'm choosing m to be large enough so that I get this to be 1/4. Well, if alpha is equal to a half, what's my effective contraction rate whenever I have this power? Well, it's going to be 1/4 to the 1/2 power, or in other words, my contraction is now, instead of being 1/4, it's just going to be a half. So I'm going to converge at a slower rate, but I'm still going to converge. Okay, so this alpha-weak property says that, well, if you have an alpha-weak approximation property for your multigrid method, you should expect maybe to get slower convergence, but you should still expect to get convergence overall. And that is, in fact, what we observe with methods that have this property. So let's do a quick proof of this, because this is brand new, but it'll also remind us of what we did to show the convergence of the two-grid method. All right, so in other words, what we're showing here is we have this type of contraction between the error at k+1 and the error at k. And we can define the error at k just to be the error of the true solution minus whatever input we throw at the two-grid method, and the error after doing the two-grid method, or the error between the true solution and the output of doing the two-grid method, with this as my starting value. Okay, so that's how K1 and K are defined in this case. So again, this is one-sided smoothing. I forgot to mention that. So one-sided smoothing, because we're setting M2 to be equal to 0. So our error transfer matrix is just this. There's no post-smoothing step, so that's gone. This is our error associated to the coarse grid projection, and this is error associated to smoothing. And somehow these two should conspire with each other so that we can produce a contraction factor which is less than 1. Now, recall that the strong Galerkin condition holds, and so that means that I minus pi 1 tilde is always a projection matrix. So Galerkin condition means that pi 1 tilde and I minus pi 1 tilde are projection matrices. It's always true, even if I don't assume that, just by the construction that I've done, that I1 minus pi 1 tilde is self-adjoint, and that's that statement. If those two things are true, then it's fairly easy to show that this equality holds. Okay, so that's all I'm doing, as I'm leading up to showing that this equality between this object and this object holds. Now, this is the statement of my alpha-weak approximation property. That's my assumed approximation property. I know that I have some CA2 and some alpha for which this holds, and even though I'm applying it on level 1 here, if this is true in general, then it's level independent, this constant. Now, why is this equal to that? Well, it's just because I can replace this with a square, and then I can move one copy over to the other side, and you'll see you immediately get I1 minus pi 1 tilde U1 A1 norm squared. So square this, and then move one of those squares over to the other side, and you immediately get this object here. Okay, so that's what alpha-weak approximation property gives us. We've assumed the Galerkin condition, so we're going to use both this and that now. Next, recall that Richardson's smoothing method satisfies assumption S1. That's our weak, or not weak, that's our first smoothing principle. And we're going to use this fact and the stability of Richardson's method. So the stability of Richardson's method just means that anytime I have a K1 tangled up in here with an A1 matrix or A1 norm, I can just remove that guy, okay, at will. All right, so if I apply my alpha-weak approximation property, I get this. But now this thing here is not so valuable to me in this form. It's this guy that I really want. It's that guy right there that I really want, and that's useful because that guy I can apply my stability property, or sorry, my first smoothing principle to. But let's take care of this guy first. All right, I'm just going to take this and remove this guy, and I can do that via stability. That K1M goes away, and I simply am left with that. Okay, so this is kind of a new step that has to be done when we have the alpha-weak approximation property. So let me write that. So that's a new step that didn't appear previously whenever, I should say, new step for alpha not equal to 1. Okay, now once I have this, then everything else is pretty cool because now I can apply my first smoothing principle to this guy. If I go back to what S1 looks like, that's a way of saying or relating this norm of an object which looks like this guy to this smoothing parameter times a product of the spectral radius at level 1 times the number of smoothing iterations. Now, each one of those is going to come with an alpha power because even though I'm applying the same smoothing property, the first smoothing principle, I'm applying it to this matrix or this vector norm here, but it comes at an alpha power. Now, it's still true. It's just that everything associated to that comes at an alpha power too. So that's all of this stuff here. Notice that each one of them has this added new alpha power that didn't appear there before. So this is all new. And so, but that's fine because I can still couple everything together in some big alpha power. I still get the cancellation of the spectral radii. That's an important feature. Still get the cancellation of the spectral radii. All right, that's the important feature there. I still get a square root of m on the bottom if I factor out this power of alpha on the top. So again, I can still make this term as small as I please. It's just that that's going to be small, but when I take the alpha power, it gets a little bit larger. Again, the example I want to use is suppose that this guy is equal to a quarter, and suppose that, so we'll call this gamma. So this guy in here is gamma. So if gamma is equal to a quarter, but alpha is equal to a half, then we come out with an effective convergence rate or contraction factor of gamma to the 1/2 power. So our effective gamma, let's call it gamma effective, becomes 1/2 because we have to take the square root of gamma. And that's it. That's all. That's the proof. It's still not that hard. But we see that some of these multigrid methods, like the self-centered approach, self-centered multigrid approach, doesn't have the full approximation property, but it has this alpha-weak approximation property. And the question for a long time was in the community was, well, do I still get convergence? And the answer is emphatically yes. You still get convergence. It's just the convergence rate may be somewhat diminished. Now, the next thing I want to point out is we next in the notes previously went on to the W-cycle, and we proved that you know, if I have if I am allowed to choose my number of smoothing parameters to be as large as I need them to be, then I can always guarantee that I'm going to have a contraction for the one-sided W-cycle. And the convergence rate was some gamma, which was evident when we were doing the proof. So I'm not going to go through this proof again. Everything here is more or less the same. The question is, can we prove the same property if we replace the strong approximation property with the alpha-weak approximation property? And I didn't know this result previously, but it turns out the answer is yes, that you can still do this for the alpha-weak case. And so this is kind of, for me, a new result. So I can still get a contraction factor of any size that I want, even if I'm using the alpha-weak approximation property. The other properties I'm using are the Galerkin condition, and I'm using Richardson's method so that I can use the first smoothing principle for that. So what are the details? The details are pretty much exactly the same as they were for the alpha-weak case. It's just that I need to use the fact that I have the alpha-weak convergence of my two-grid method. And if I have the alpha-weak convergence of the two-grid method, I can use the same strategy that I used to prove the W-cycle convergence. And what I can show is that, in particular, if I choose M to be this large, okay, larger than this number here. I think this is a typo though. That should be, 2 should be here, a square. So that is a typo that I need to fix. So that should be a power. This 2 should not be here. It should be elevated to the power up above, as shown. But if I choose M to be bigger than this number, which I can always do, then I'm going to have the desired contraction factor of gamma, whatever that is. The only difference between what I do here is now I have an alpha. Okay, so now I have an alpha. So let's see. Alpha is, let's think about this. This number and this number, the difference is going to be a small number, right? Because this is the contraction factor that I want. That's some small number less than 1. Alpha to the p is, because we're using the W cycle, p is equal to 2 or 3, something like that. So let's suppose that p is equal to 2. So this is gamma minus gamma squared. So that's a pretty small number. Over this number, this can be large. Usually it's an order 1 number though, so that's good. But this could be large. Now what happens as I take the 1 over alpha power of this number here? Okay, this number is small, but when I divide by it, it becomes a large number. That's what I'm saying. So this number is overall small, but if say alpha is equal to a half, then this means square that result. So it becomes even smaller. So again, we're winding up with the fact that, well, it may require more smoothing iterations to achieve a contraction factor that we desire. But we can eventually get there, even if we have this weaker alpha-weak approximation property. So this one I really did write as an exercise, and those of you who made it this far have noticed that this is a new exercise. But the good news is the proof is more or less exactly the same as the W cycle proof. You just have to use, instead of the convergence of the two-grid method in the classical case, you have to use the alpha-weak convergence of the two-grid method. Okay? And so those are all of the changes that I wanted to mention that are present in the notes, and I hope that they don't change going backward anymore. Things will still change going forward as usual, because as I'm going through the slides, I find typos and things like that. But yeah, I hope there aren't any more retroactive changes. I don't think there will be. But I thought that was simple enough that let's put it there and get it over with and get it changed. All right, so now we want to get into chapter 6, where we apply the multigrid method to the finite element approximation for the Poisson equation. The idea here is that we've already taken care of all of the theory for the convergence in the previous chapter, chapter 5. So now all of chapter 6, it's going to be a kind of short chapter, and it's in some ways kind of anticlimactic, because we've already proven everything that we wanted to show. All of the convergence results that we wanted to prove, except for one, are already completely taken care of. There's nothing for us to do, which is kind of a letdown in some sense. But it's going to be nice to see how this applies to the finite element setting. So that'll be a brand new thing for us. So there are two slide decks for this chapter, and we're going to start with part one, of course. Why not start with part one instead of part two? So let's remind ourselves what we're trying to solve here. So what I want to solve is this problem. Minus Laplacian of u equals f in some nice, whatever that means, domain omega with u equals 0 on the boundary of omega. Now, we're going to do the usual thing, as we've done in other classes. For example, in numerical analysis, we multiply by a test function, integrate by parts, and we create a weak form of this problem. And the weak form is precisely here. So and so we can tailor this problem as slightly differently. Here we're saying find a classical solution u, which is twice continuously differentiable, such that it satisfies this equation pointwise and these boundary conditions pointwise. Okay, so that's called the classical problem. You're given some nice function f, and you're supposed to find u. In the weak formulation of the problem, we can write it this way. Given f, an L2 function, find u, a function which is in H01. This is the H01 Hilbert space, which we'll talk about momentarily, such that AU V equals FV. Okay, for should have said, and I failed to do that, for all V in H01. So that's missing, but should be there. Where, what is this? This is our bilinear form A, and it's equal to the gradient of U against the gradient of V. So if you've taken numerical analysis, you've seen this, and we emphasized it a lot in the second semester of numerical analysis here at the University of Tennessee, and so you're probably really familiar with it. If you haven't taken that course from either Dr. Salgado or myself, but maybe you've taken another course in PDE, then you've seen this, or in the finite element method, which here at University of Tennessee is 574. By the way, I'm going to teach that course in the fall of next year, so at least I'm signed up to do so. So if you haven't taken finite element methods yet, and you want to learn more about those, then I'm going to do that in fall of 2025. Wow, 2025. In any case, this is the weak form of this problem here. Strong form, weak form. Okay, or I should say here is the weak form. Finite element method is based on that. Now, what is this space H10? That's a Hilbert space, and that is the space of all functions, which are L2, such that they also have a weak derivative on omega that is also an L2 function. All right, so sometimes we write that like this, H1, and I'm going to add on the 0, and I'll talk about the 0 in a second. So that is the set of all functions v in L2, such that the weak derivative, okay, so the weak derivative is also an L2 function. Now, if you know anything about gradients, you'll know that those are actually vectors. Those are vectors, right? So actually I have to put this around it and say each one of the components is an L2 function. Okay. And by the way, I should say this means that the weak derivative exists and is an L2 function. So there's a bunch of words here. The weak derivative exists and is an element of L2. So I'm skipping over the exists part, and I'm just going, the weak derivative is an element of L2D. And U equals 0 on the boundary. Now, those of you who know anything about PDE analysis know that these functions, which are defined to be a part of a Sobolev space, don't have point values. So what does it mean to say that u is equal to 0 on the boundary? Well, what we formally mean is the trace of u, and the trace of u is an operator which acts on u and it maps u into its values, or what it should, it's what I'm going to call the should be values on the boundary. And those should be values should in this case be all 0. So that sometimes we'll replace this by an operator called gamma 0. That's the trace operator. Okay, so the gamma 0 trace is 0 on the boundary. But that's too much formality for us. So we're simply going to say u equals 0 on the boundary. So that's what this set is here. It's a Hilbert space. And notice that the test function has the same boundary conditions as the solution to the problem, the weak solution. By the way, if we can find a solution like this, we call it a weak solution. This has a lot less requirements about the smoothness on it than this problem up here. This requires two classical derivatives to be, it requires two classical derivatives to exist and both be continuous on the domain, whereas this one only requires weak derivatives. Okay, so I'm going to get off the soapbox talking about the weak formulation and finite and why it's the setup for finite element method, and I'll get right into the details of that. Now, here for multigrid, we're going to do things a little bit differently than we usually do for finite element method. So usually for the finite element method, you probably remember, you start off with your domain and you cut it into a bunch of triangles. All right. So we cut a domain into a bunch of triangles. Here, we're going to go even further. We don't want to just cut it into one subsection of triangulation. We want to compute a whole nested family of triangulations of this problem because we need this for our multigrid strategy. So that's what we're going to call a nested family of finite element spaces. So let T0 be a conforming triangulation of some domain omega. This means that there are no hanging nodes. So what we mean by a hanging node was explained in the numerical analysis course, but let me remind you what that means. It means that we have no situation like this. So if we have a neighboring triangle or set of triangles, then this can't happen. We can't have this node here being in the middle of a full edge of another triangle. Or in other words, if we look at it like this, anytime we take an edge of one triangle, then it's either going to be shared by the edge of another neighboring triangle or a boundary. In this case, we see that that fails because in this one, it's not a conforming triangulation. The edge of this triangle here is not a full edge of this triangle over here. Likewise, if we take this edge here, it's not the full edge of a single triangle over here either. It's the edge of two triangles. So this can't happen. This is what we call a hanging node. And so the way we fix a hanging node, there are a lot of ways to do it. You can make a connection like that, or you can just say that, well, maybe these two things started out in this primordial sense where I didn't have any hanging nodes. And the way I'm going to refine both is I'm going to quadrisect both. And quadrisect means all you do is you connect up the midpoints of all the edges. And as long as you quadrisect in the same sort of manner, then you always have a triangulation which has no hanging nodes. Okay, but that's in the way of a review from numerical analysis. All right, now if we refine, we're going to define T1 to be the triangulation of omega that results from bisecting our triangles, quote unquote, or quadrisecting our triangles in the triangulation T0. So I want to show you how this goes. So in one dimension, here's a triangle. So, or an element. Okay, so this isn't a triangle, but it's sometimes called a triangle or an element. So we're going to bisect that by just cutting it into two and making two new intervals, which are half the size of the previous. So you can see that I obtain a triangulation, or I obtain from T0, I obtain this triangulation T1 by adding these bisection points. So this element gets bisected here to create two child elements from this parent. This parent element here creates two children through bisection, one here and one here. Okay, and they're clones of each other. They're similar clones. How do we do this in 2D? So in 2D, let's, for example, take, I've already explained it, but I'll show you again. Let's take this triangle. Okay, so here's a T0 triangulation with no hanging nodes. And what we're going to do is we're going to place each triangle with 4 children triangles. Okay, so each parent is going to create 4 children. 1, 2, 3, 4. And you see the way we did that was we just connect the midpoints. We have to do this with every triangle, with every parent triangle creating 4 children triangles. So you can see how this guy here is now going to become these 4 triangles here. Okay, so each parent creates 4 children. This is what's called quadrisection of a 2D triangulation. So T0 is this guy, T1 is here. If we continue this process, you can see that this can be done recursively. Now I could refine these triangles, right? And I could keep going. If I do this recursively, then I obtain this full family of conforming triangulations. Conforming means there's no hanging nodes. I hope everyone sees that. If I continue this process sort of going upward, then I'm going to get a finer and finer mesh going upward. So let TL, L equals 0 to capital L, be a nested family of triangulations of omega. I hope that you agree that that can be done. And triangulation, I should probably put in here that they are conforming triangulations, so no hanging nodes. Okay. For 0 up to capital L, let's define the grid spacing, HL, via the following prescription. HL is equal to the maximum taken over all of the triangles in the triangulation of the diameter of the triangle. So what you do is you take the diameter of each triangle. So the diameter of the triangle can be kind of computed in one of 2 ways. The way I like to think of the diameter, you can think about it as the diameter of the smallest ball or the smallest circle which fits around the triangle. Or you can take it simply to be the longest edge in any triangle. Okay, that gives you a measure of the diameter. So for the diameter of this triangle, well, it looks like in this case it's not quite. It's in a projection. So this should be a square in projection. So if this has length a half and this has length a half, then this is equal to the square root of half. Or let's see, it's Pythagorean theorem. It's longer than that by a factor of square root of 2. All right. So that would be this length would give rise to the diameter of this triangle. But notice that this triangulation was gotten by starting with a square. This whole big thing here is a square. All right. It's in projection, so it doesn't quite look like a square. I should have written it like this. So it's you kind of have the x-axis coming out this way and the y-axis coming out this way. So it should be thought of as a square. In any case, all of these triangles are similar triangles, and moreover, they're the exact same size, and so their diameters are all the same. So it doesn't matter if I take the max or not, I'm always going to obtain that this guy here, this length here, is the h for T0. So h0 is the length of this. Now, what about h1? Well, again, all triangles are going to be the same. They're going to they're similar triangles. They have the same diameter, and the diameter is given by that length there, which is going to be 1/2 the diameter of this guy. So the diameter in my triangulation always goes down by 2, right? So that's how I get the mesh spacing or the grid spacing at each level in my triangulation. Remember, now I have a family of triangulations because I'm going to quadrisect going all the way up. Now, subordinate to these triangulations, we're going to define a finite element space, VL, and it's defined in the following way. So VL is the set of all continuous functions such that on each triangle, these are linear functions. So linear on each triangle, okay? For every triangle in the partition or the triangulation, such that, or with the requirement that the function has to be 0 on the boundary. Now, this function, we have to know, do functions like this even exist? Is there a globally continuous function such that when I restrict it to every triangle, I have a linear function? Can I actually get a non-trivial function in this space? And the answer is yes. And one of the requirements of not having any hanging nodes, or in other words, having this be a conforming triangulation, is so that we can build this in a reasonable manner and show that there are non-trivial elements in this finite element space, which we're going to do next time. So we're going to stop here, and we'll get into more depth in the finite element method when I see you again on Thursday.